We present Instruct-CLIP, improving instruction-guided image editing with automated data refinement using contrastive learning. Instruction-guided image editing models provide an intuitive interface by requiring only a single edit instruction in natural language, whereas prompt-guided methods depends on both input and target prompts. However, automatically generated training data for these models often contains misaligned samples, where the visual change between the input and edited images does not match the provided instruction, leading to degraded model performance. While pre-trained vision language models can be used to correct such misalignments, they often generate overly verbose prompts and suffer from hallucinations. On the other hand, manual dataset curation yields high-quality results, but is expensive and does not scale well. To address these limitations, we propose Instruct-CLIP, or iCLIP in short, a method that operates directly on existing datasets, enabling them to self-correct misaligned samples and generate more accurate edit instructions. This ultimately leads to improved performance of editing models trained on these datasets. Although some data suffer from misalignment, the datasets overall still contain valuable signals that we aim to leverage to enhance instruction quality. To extract a valuable signal, we use iCLIP Vision Encoder to encode the visual change between the original image IO and the edited image IE, producing a visual change embedding ZVIZ. We also encode the edit instruction P into a text embedding ZText using iCLIP Text Encoder, which is a pre-trained CLIP text encoder. Both embeddings are mapped into a shared feature space using a contrastive loss L contrast, similar to what was done in CLIP. To convert iCLIP embeddings into more accurate edit instructions, we adopt the decap approach by using a decoder to translate embeddings into text, which is trained to reconstruct P from ZText, avoiding mismatches during training. At the inference time, our goal is to decode ZVIZ into an instruction that faithfully describes the image visual difference. To align with the decoder's training distribution, we project ZVIZ into the text feature space by computing a weighted average over all instruction embeddings in the dataset, where weights are determined by cosine similarity to ZVIZ. The resulting projection is then decoded into a refined instruction P prime. We now describe the architecture of the iCLIP Vision Encoder. For the iCLIP Vision Encoder, both the original and the edited image are processed by DynoV2 model to extract visual features. The resulting features are then subtracted with one another to capture their visual difference, which is then passed through a standard CLIP Vision Encoder to obtain the embeddings representing the visual change between the images. Beyond finding training data, we also want to integrate iCLIP into the process of training image editing models. Since these models often operate in the latent space of Stable Diffusion VE encoder, to use iCLIP during training, its DynoV2 backbone needs to operate in the same latent space. Furthermore, since these editing models work with noisy images generated through forward diffusion, the DynoV2 also needs to remain robust to noise. Therefore, we train a latent diffusion-compatible version of DynoV2, referred to as LD DynoV2, on the VE-encoded latent images with diffusion noise, which serves as a perceptual loss function to train editing models. With our approach, we are able to refine editing instructions in existing datasets, such as Instruct-Pix2Pix. To evaluate this refinement, we compute the cosine similarity between the image visual change embedding and the edit instruction text embedding. Our results show that the refined instructions exhibit higher cosine similarity, indicating better alignment. Furthermore, our approach improves the performance of image editing models trained on refined datasets, demonstrating the practical benefits of instruction correction for downstream editing tasks. For more information, please visit our project page. Thank you.